Now I'm going to briefly run through the different confidence intervals that we'll be looking at in this chapter. Not the first one up, but the first one I have written here are confidence intervals and sample sizes for proportions. For the population proportion, we're going to use the symbol P. And for the sample proportion, we'll use a P with a little caret on top, and we read that as P hat. P hat is our sample proportion. Some problems we may have the X value, the number of sample units that possess the characteristics, and we always have to know the sample size. A proportion is a percentage. For a sample proportion, P hat is given by X divided by N, and then we can calculate Q hat exactly the same way that we were doing P and Q for the binomial distribution. Q hat is 1 minus P hat. An example, in a recent survey of 200 households, 143 had broadband internet. We want to find P hat and Q hat, where P hat is the proportion of households that have broadband internet. So in the problem like this, N is our sample size, 200. X is the number of people who have broadband internet, the number of households that have broadband internet. So P hat given by X divided by N, which would be 0.715. Q hat is 1 minus P hat, which would be 0.285. For confidence intervals for proportions, we're drawing on the section just at the end of chapter 6, talking about how a normal distribution can approximate a binomial distribution. This is the idea right here. We see that P and Q pop up just like with a binomial distribution. We can think of a proportion situation as being binomial. Either they have broadband internet or they don't. So we have two outcomes. We have a specified probability. The outcomes are independent. There's a fixed number of trials with 200. Proportions follow a binomial distribution, but binomials get complicated when we get really big. So instead of a binomial, we're going to use the normal distribution. There's a formula for a confidence interval for a proportion. Notice our friendly n times p and n times q need to be greater than or equal to 5 or greater than 5, depending on the book. But I'll break down this formula here and we'll talk about the pieces. First off, you should see two repeated objects, two repeated expressions, which I'm going to highlight in yellow. These two repeated sections right here that are identical, this is called our margin of error. And notice we add and subtract that margin of error to the sample proportion. And in the middle, we've got our population proportion. So this is creating the interval using our inequality symbols for the structure. Excel and Google do not contain a formula for calculating confidence intervals or for margins of error. Most technology calculates the margin of error, and then you have to take the margin of error and add and subtract from the sample statistic. But in the case of proportions, Excel and Google don't even have that formula built in. So we're going to use a template that has been created and will be posted to Canvas. So it will help you with this calculation. You'll need to make sure you put the values in the correct cells to calculate the confidence interval, and I will show you how to do that in one of the subsequent examples. The notation inside the margin of error, we have a very particular symbol, that z alpha over 2. So this guy right here is z alpha over 2. This is a standard normal value that represents the z value with probability of a over 2 to the right. The z alpha over 2 is a z value that cuts off the normal distribution away from the tails. So the example in the picture, if alpha is 0.02, then we have 0.01 in each of the tails. So if our alpha over 2 is 0.01, we have 0.01 to the right, which means we have 0.99 to the left. And if I calculate that, in Excel, I get 2.3263, and we usually round to 2 decimal places. So we have 2.33. And because our standard normal is symmetric, over here we have negative 2.33. But that negative, ultimately, we don't need because we're subtracting already. We don't need another negative caught up in there. So we'll use the positive value in our margin of error formulas. And for confidence intervals, we always use alpha over 2. We split the alpha in half and give each tail half because we're looking on both sides of the population parameter. We need to take off equal amounts of probability from both sides of the distribution. We can also talk about sample sizes. One thing that's kind of really interesting when you think about it in regards to confidence intervals is that if we want to create a confidence interval estimate for a population proportion, and we need to know how big of a sample do we need to collect, then we can actually take the margin of error formula and rearrange it using some algebra and solve for n. And n is our sample size, which is pretty crazy if you think about it. When we're looking for sample size calculations, and minimum sample size means this is the smallest sample size I can take and still be 95% confident or 99% confident or whatever our confidence level is. So this is the smallest sample size we can take in order to have that confidence. We could take more, but that number's the smallest. An example, a researcher wishes to estimate with 95% confidence the proportion of households who have broadband internet. A previous study shows that 80.4% of those interviewed had internet at home. So the researcher wishes to be accurate within 2% of the true population. Find the minimum sample size necessary. We have our confidence level. Alpha will be 0.05. A previous study, we're going to let that be our p-hat. The researcher wishes to be accurate within 2%. This is our margin of error. If we know P, we automatically know Q. If we know P-hat, we automatically know Q. 1 minus P-hat will give us Q-hat. And we'll need to find the corresponding z-value for alpha equals 0.05. So norm.inv, 1 minus our alpha was 0.05, and I'm going to divide by 2. So I'm forcing Excel to calculate the area to the left of my positive z alpha over 2. Our alpha was 0.05, cut it in half, subtract it from 1. And I forgot my s in there. Need to make sure we're doing standard normal, and we get 1.96. So we can take these values and substitute them into this formula. N equals 0.804 times 0.196 times, big parentheses, 1.96 over E, 2%, we're going to change it to a decimal, 0.02 squared. And either in your calculator or in the spreadsheet, we can calculate this. You could even make Excel calculate Q. And I think I forgot a multiplication, so I'm going to make sure I put my multiplication in there. Times, big parentheses, 1.96 divided by 0.02 squared. And that will give us 1,513.4. But we always round up. Always up. that 0.4 of a household, we want to make sure gets covered. So we have to round up to the next whole number. If we were to take a sample size of 2,000, that would be sufficient for our 95% confidence level. But if we were to take a sample size of 1,000, it would not be sufficient. We don't have a sample size big enough to guarantee that confidence. For proportions, we kind of have another little special quirk about them. If we know nothing about a proportion estimate, then we can assign p hat and q hat to be 0.5. If I take any two numbers that add up to 1 and I multiply them together, the biggest product of all of the numbers that satisfy that characteristic will be if those two numbers are 0.5 and 0.5. Think about it. 0.4 times 0.6 is 0.24. So if we try to change one value to make it higher, we automatically decrease the other one to make it lower. All you need to know from this is if we know nothing about a sample proportion estimate, just use 0.5 for P and Q. If we know no prior knowledge, then that's going to cause our minimum sample size to increase. If we were to repeat the problem from before, instead of putting in 0.804 and 0.196, if we replaced it with 0.5 and 0.5, we're going to get a number much larger than 1,514. You could try that on your own if you want to. But let's see if we estimate the proportion of teachers who own a laptop and we want to be 90% confident, which means alpha is 0.1, and to be accurate within 5%, that's going to be our margin of error. And this time I don't have a p hat and a q hat, so we're going to let p hat and q hat be 0.5. We need to calculate our z alpha over 2. Norm.s.dist 1 minus alpha was 0.1 and we divide by 2. That's not right. It's not .dist. This is a norm inverse function. 1 minus 0.1 divided by 2. And we get 1.6448. And we usually round this to 1.645. I know it's a little bit awkward because it's 3 decimal places. Or you could just 1.64. And we're going to plug it into that same sample size formula. N equals P times Q times 1.64 over 0.05 squared. And I can do that here in Excel. 0.5 times 0.5 times big parentheses 1.64 divided by 0.05 squared. And we get 268.96, which would round up to 269 in our sample size. A lot of things changed from this problem compared to the previous one. We lowered our confidence interval and we lowered our accuracy. We increased our margin of error. We're allowing the error to be bigger. And by doing that, it causes our sample size to get smaller. Even though it's not the same type of problem, we're still trying to estimate a proportion. And that wraps up our discussion on proportions. Next up, we'll talk about means and how to find confidence intervals and sample sizes for that. I'll do the confidence interval calculations in the examples that are tied to the textbook. So take a look at those examples to get confidence interval calculations. We'll be using the spreadsheets to do the calculations, but it really comes down to interpreting what that confidence interval means.